So, hello everyone. I'm Gitanjali Jaina. I'm a PMR scholar from IIT Delhi, and I'm also a teaching assistant for this course, which is Introduction to Laser. So, the basic motive of this course, this live section is to uh, go through the concept that has been taught during this week, as well as uh, also solve few problems related to the concept. As well as I will clarify the doubts that you must be having for the assignment, as well as the conceptual doubt. And other than that, you can also ask me any doubts that you must be having during the course. And okay, let's wait for 2 minutes more so that others can join. Then I will start the section. Before starting the conceptual concepts of this week, let me ask whether you have any doubt in the current assignment. Sorry, the in the assignment 4. The solution has been released in the NPTEL site. So whether you have any doubts in the assignment, you can ask me now. In the meantime, I will go through the doubts you must be having in the assignment. Then we'll start the normal section. Let me unmute you. Otherwise, you can also write in the chat box. So let me ask again whether you have any doubts in the assignment and the solution of the assignment 4. Let me write in the chat box also. Let us go through the doubts you must be having in the assignment, and we'll start the section after a few minutes. Mm. Please free to ask me any question that you must be having or any doubts. The live section, you can ask your doubts. You can clarify your doubts as well as uh, if you have any problems in the assignment. If you're getting any other answer that has been posted, then you can also ask. I will try to answer that. Otherwise, if I don't have any answer, then I will address it in the next live section. Either use the chat box or you can let me unmute you. Or you can ask me directly by muting yourself. Sorry, unmuting yourself. So the solution of assignment 4 is already being released. Everyone can see the solution. Yes.
मैम ये जो असाइनमेंट 1 था उसमें एक
हाँ
क्वेश्चन मैंने रेज किया था जो आंसर वाला मैम उसका कुछ सॉल्यूशन आया कि नहीं?
हाँ, वो अभी ट्राई कर रहे हैं। मतलब हमने बात किया है सर के साथ, तो इधर वो क्वेश्चन को ही हटा देंगे क्योंकि उसमें एम्बिग्यूटी है। सॉल्यूशन बहुत सारे आ रहे हैं क्योंकि आंसर का ऑर्डर बहुत आसपास था, तो इसीलिए थोड़ा कंफ्यूजन था। तो वो एड्रेस हो जाएगा, थोड़ा टाइम लगेगा क्योंकि ऑलरेडी वो वेबसाइट में ऑलरेडी पोस्टेड है, तो थोड़ा टाइम लगेगा वो सॉल्यूशन वो क्वेश्चन को सॉल्व करने। हो जाएगा, सर को
ओके
बता दिए हैं, तो सर इस बात
ओके ओके थैंक यू
ओके।
मैम।
Any doubts in the assignment 4? Okay, if you don't have any doubts, then let us start the section.
मैम क्या ये जो ये फिफ्थ जो है यूनिट जो अभी पोस्ट हुआ था जो रिसेंटली, क्या उसके कुछ डाउट्स पूछ सकते हैं या जब डिस्कस करेंगे तभी होगा?
डिडंट गेट इट। फिर से रिप्लाई, सॉरी, फिर से रिपीट करो।
मैम ये पूछ रहे हैं कि जो अभी लेक्चर जो है फिफ्थ लेक्चर पोस्ट किया गया है, तो मैम उसके
हाँ
रिगार्डिंग अभी पूछ सकते हैं या जब डिस्कस करेंगे तब?
हाँ, आज तो मैं वीक 5 का भी पढ़ाऊंगे तो तब मैं डिस्कस कर सकती हूँ, उसके रिलेटेड भी पूछ सकते हो तुम, क्योंकि हम वीक 5 का ही कंटेंट देखेंगे, तो यू कैन आस्क मी एनी डाउट इन द वीक 5 कंसेप्ट।
मैम एक डाउट ये था, जैसे फाइनेंस की हम बात कर रहे हैं, तो फाइनेंस में हम जैसे एक है कि हाई फाइनेंस की बात कर रहे हैं, तो क्या हमारा जो राउंड ट्रिप वो होगा कि हम हाई फाइनेंस का फार्मूला यूज कर सकते हैं और कब हम नॉर्मल फार्मूला यूज करेंगे?
So fineness is very, matlab you can define fineness in various ways. Like there are many formulas to define the fineness. It's actually related to um, the house or the package. So depending on the question, you can, on depending on the situation, you can apply any of this. Just go through the question, what is given, what is already given, what are the parameters that is already given. From that, I think you can easily solve it. So
एक्चुअली
we'll
मैम
go through finance today. हाँ
एक्चुअली मैम we have finance 0.90 to 0.98 रेंज और हाई फाइनेंस। तो मैम अगर न्यूमेरिकल्स आते हैं, अगर 0.90 फाइनेंस दिया है तो हम नॉर्मल फार्मूला यूज करेंगे या हम हाई फाइनेंस के लिए जो फार्मूला है वो यूज करेंगे, या दोनों में से कोई कर लें तो वो हो जाएगा?
ओके, जो नॉर्मली क्वेश्चन आते हैं, मतलब if you consider the normal laser optical laser resonator, then what we see, the fineness is very high. Like for normal situation, the day-to-day situation, it's very high. So for that case, you will use the approximated formula. Don't use the actual formula, but do use the approximated formula. So in the problem in the problem also, it will be given that it is of high fineness, or that if it is a normal laser that we are using nowadays, then it is high fineness. So for that you can use the formula. I think, let me show you the. So you are talking about think. So you are confused whether in which situation what formula to use, right?
Yeah.
So normally for it is normally whatever the question will be given, then it is of high fineness. That is, f is much greater than 10. So for that you can use the fineness formula, that is sin inverse pi by. You can approximate it. The sin inverse is pi by 2x. Otherwise, if not, then in the question also they will mention ki don't use the approximate formula. They will mention something. Hint will be given in the question.
Okay.
But in normal situation, we can use the approximated formula. Okay.
Okay. Thank you.
Okay, so let us start the section. So basically, we'll go through the problem. Can you mute yourself? Okay. So we'll go through the concept, as well as we'll go through problems that is related to ADFA in today's section. And also we'll go through the different types of resonator. So in the last section, we're talking about EDFA, right? So EDFA, depending on the kind of pump, 1 minute. So depending on the type of pump, like if it is 980, if it is 800, and if it is 1480 nanometer, then we can describe the EDFA as either quasi 3-level system or quasi 2-level system. So if we use a pump 1480 nanometer, then we can visualize the EDFA as a quasi 2-level system, and otherwise, if you use 980 or 800 nanometer, then we can describe the EDFA as a quasi 3-level system. So if you see the energy level diagram of EDFA, so we have a ground state which is 4i 15 by 2, one metastable state which is 4i 13 by 2, and one excited state 4i 11 by 2. So when we use 980 nanometer pump, what will happen? The erbium ions that is doped in the optical fiber, they will get excited to the higher excited state. Okay, they will excited to this higher energy level, and from that level, they will rapidly decay to the metastable state, and they will stay. The erbium ion, they will stay for a longer time in the metastable state because the metastable state, they do not follow the selection route. So the transition from that level is not usually allowed. So that is why what will happen? The population in the metastable state will gradually increase over time, and we will see a population inversion between the metastable state and the ground state. So metastable state here is the 4i 13 by 2, and ground state is 4i 15 by 2. Now, to make a transition from this metastable state, what we'll use? We will use a weak signal, which is around 1550 nanometer. If we use a weak signal, then what will happen? This weak signal will stimulate the transition from this metastable state to the ground state, which is 4a 15 by 2. And in this way, we will see a stimulated emission between this energy level, and the weak signal will get amplified in this quasi 3-level system of erbium doped fiber amplifier. So previously we have seen for a non-degenerate system, we can approximate the scattering cross section. So please remember this small approximation that we are using time to time. So this will help you to solve the problems. So for non-degenerate system, we have both the scattering cross section sigma E is equal to sigma E. So for this case, where the gain, we can write the gain is gamma is sigma times delta M. And if we want population inversion in this non-degenerate system, then what is the condition we have? We must have delta N should be greater than 0 for the non-degenerate system. That is, the N2, the population in the metastable state, must be greater than the population in the ground state. But when we are seeing that in EDFA, there is a Stark effect. That is because the glass is a periodic crystal, that is amorphous. If you know, it is amorphous material. So arrangement of atoms in the glass matrix, it is not periodic. So when you dope with the erbium ion, then we will see there is a density of the erbium ion. It will change, or if you see the distribution of erbium ion in the lattice, then we'll see there is higher density in some region and lower density in some other region. And because of that, we'll see a multiplets of energy level. So we can't approximate as a non-degenerate system. So for degenerate system, what we have? The gamma, that is the gain. You can write it as sigma E N2 minus sigma E N1. So in this case, what is the condition for population inversion? So population inversion condition is gamma should be greater than 0. So that means this term sigma E N2, it must be greater than sigma n1. So, one parameter that we can define is the quantum defect for this case. So, quantum defect, if you see, it's a ratio between the energy of the amplified signal to the energy of the pumping signal. So, it is h nu L divided by h nu P. And if you write it in terms of wavelength, it is lambda P divided by lambda L. So, normally this value is always less than 1. Okay, because the lambda P, it is of pumping is wavelength is smaller than the emitted wavelength. That is the amplified signal. And what does this quantum defect signify? So the quantum defect it signify how efficient the optical amplifier is when we use a pump. So it signify the pumping power, pumping signal efficiency. So for the better amplifier, what we must have the quantum defect. It must be closer to 1. So it means that if it is closer to 1, that means the energy that is radiated in form of heat. So if you see here, so in the laser, in a 3-level system, we use a pump to excite the ions to the higher excited state, and from that state, it radiate in terms of non-radiative transition. So there is a release of energy in form of heat or any lattice vibration or any other means. So if the quantum defect it is much close to 1, it means uh, this energy that is lost in form of heat or lattice vibration, it is much less. So that means most of the pumping power energy it is utilized to amplify the signal. Okay, so if you are given different quantum defect, then you can easily identify what is the best pump to use in a given uh, EDFA medium. Okay, so the higher the quantum defect, the better is the pump. And this is the schematic of a scattering cross section. So as we see, the emission cross section is not always equal to the absorption cross section. So if you see the blue curve, it is for the scattering cross section of absorption, and this is for the red curve is the scattering cross section for the emission process. And normally these are not equal. So depending on the wavelength, so depending on the amplified wavelength, if you see a wavelength around which is less than 1550 nanometer, here you are seeing the sigma A. In this region, the sigma is much greater than sigma I. So for amplification, so the condition here, it will be different than the condition here. So normally for the gain, what should you have, we should have, it is gamma I should be greater than 0. That is sigma E N2 should be greater than sigma I N1. Okay. So depending on this value, sigma I and sigma I on either side of 1550 nanometer, the N2 and N1, it will vary. Okay. And if you see the schematic of EDFA, so it is this components that is a fiber which is used as a gain medium, and it is doped with erbium ion, Er plus Tr. So there is a fiber which is EDFA, and there is a pump that is used to amplify signal. So you use 980 nanometer pump to amplify the weak signal 1550 nanometer. And to couple this two signal, that is pump signal and the weak signal, we use a WDM, wavelength division multiplexer, to couple this signal to the erbium doped fiber amplifier. And there is a isolator. So isolator is used. So the normal function of isolator is to minimize the back reflection. So what does the isolator do? It only allow the propagating wave to propagate in one direction and it blocks the other propagating wave. So it doesn't allow this wave, and it allows the propagation only in one direction. So in this way, we can minimize the noise in the system as well as any signal interference. So that's why you use isolator in the system. And so these are the some basic components, that is EDFA, coupler, pump, and optical isolator. So this is the same schematic, but so if you see, this is the erbium doped fiber, which is approximately of 10 nanometer, sorry, 10 meter. And we couple this pump laser, that is 980 nanometer, as well as the signal, which is 1550 nanometer, by using a WDM coupler. So we'll see what is this WDM coupler. And when you couple this two signal to the erbium doped fiber amplifier, we'll see an amplified signal in the output. Okay. And normally, these are some basic characteristics of EDFA. So EDFA is a single mode fiber for both 980 nanometer as well as 1550 nanometer. Okay. So by single mode, it means, so fiber can be of many types. It can be single mode, it can be dual mode. So single mode means it only allows propagation of one mode. That is the fundamental mode. So if you know, you must have known what is the fundamental mode of fiber. It is a Gaussian wave. That is where the energy is mostly confined in the core and it decay evanescently away from the core. So for both 980 and 5050, it is a single mode. It behaves like a single mode fiber, so that most of the energy of this 980 and 1550 are these are localized in the core layer. And if you see the absorption is around 5.5 dB per meter. And the mode field diameter, it basically tells us about the extent of energy in the core layer. So the fundamental mode is a Gaussian wave. So if you see, it's a Gaussian wave. So what so mode field diameter, it is defined around the level where the amplitude is 1 by E of the maximum amplitude. Okay. So so this is the mode field diameter, which is, if you see the formula, mode field diameter is 2 times of W0. So W0 is the spot size. So if you are given a spot size of the laser, you can easily find out what is the mode field diameter. So mode field diameter is 2 times of spot size. Okay. So next is the WDM. Let us see what is the WDM coupler. So the WDM coupler, so it is WDM is wavelength division multiplexer. So if you see this figure, this is the schematic of WDM coupler. So it basically consists of two fibers, two independent single mode fiber, that is fused around a region. Okay. So if you see, this is the first fiber, and this is the second fiber, which is fused around this length, fused region. So and this length decide this fused region length of this fused region. It will decide which wavelength will come around this port and which wavelength will come around this fiber. So this length of this fused region, it decide what wavelength will come out through this fiber and what wavelength will come out through this fiber. Okay, so it basically separates out the wavelength, or it can also combine wavelength in a single file. So if you see the first one, where we incident both lambda 1 and lambda 2. So lambda 1, lambda 2 are nothing but, one is the pump laser, which is 980 nanometer, and other one is the amplified signal, which is 1550 nanometer. So if you couple this lambda 1 and lambda 2, what will happen? So it will propagate through this single mode fiber, and in the fused region, because of interaction between these two fiber, So what we'll see, you will see in the output, you will see that the lambda one, that is, let's say lambda one is 1550 nanometer. So lambda one is 1550 nanometer, and let's say lambda two is 980 nanometer. So depending on the length of this fuse region, we see that lambda one, it will come out through this fiber one, and lambda two will come out through this fiber two. Okay. Similarly, if we reverse the path, that is, we couple 1550 nanometer. Hello, so let me take a different color. So if we couple this lambda one through this fiber and lambda two through the second fiber, what will happen? This lambda 1 and lambda 2 will come out through this first fiber. So there is no wavelength around this, around the second fiber. Both the wavelength, both the signal will come out through this uh, first fiber. So this is the basic functionality of a WDM coupler. So this slide, it is also the same. It tells the same concept, that is, if you input this lambda 1 and lambda 2 through this WDM coupler, depending on the length of this coupling region, what will happen? Both lambda 1 and lambda 2, it will come out through this output end of this first fiber, and there is minimum energy, that is that will come out through this second fiber. So we'll see 98% of this input power will be coupled through this output end of this fiber. Okay, so it basically it combines two wavelength, or it will separate this two wavelength. So this is what a WDM coupler will do. And the function, the performance of a WDM coupler, it depends on this length of this coupling region. So if you change the length, this percentage, the initially it was 98 and 2%, right? So if you change the coupling region, it this percentage will also change. So depending on the coupling regions, you can manipulate the power that is coming out through this output. So this is what a WDM coupler do. So we use WDM couplers to in ADFA to couple this signal power as well as pump power to the ADFA fiber. Okay. Now we'll see. So when we couple both lambda 1 and lambda 2 in the EDFA, it's not like the pumping power and signal power, they will remain constant as they propagate through the EDFA. So the power, it changes over the length of the fiber. So if you take this figure, it's the EDFA, it's a schematic of EDFA fiber, and let's say the yellow one is 980 nanometer, and the blue one is 1550 nanometer that you are going to amplify. So we see that the pump power 980 nanometer, it is required to achieve the population inversion. So it is absorbed by the system. So if you have a 3-level system, this 980 nanometer is absorbed by these ions to achieve a population inversion in between this metastable state and a ground state. So what will happen to the power then? It will decrease exponentially as they propagate through this fiber. So because of the absorption, we will see the pump power. If you see the red curve, the pump power will decrease over the length of the EDFA fiber. In contrast to this pump power, the signal power. So if you are seeing, we are incidenting a weak signal, but this weak signal, it stimulated emission between the metastable state as well as the ground state. So what will happen to the signal power? The signal power now increase over the length of the fiber. So if you see the blue curve, the signal power, it is gradually increasing over the length of this fiber. Okay. So signal power will increase over the length of the fiber. Now we'll see, if you want to find out what is the gain in a medium. So it's a schematic of a EDFA fiber, so there is a core which is used as a gain medium and it is doped with erbium ion. And there is a cladding. So because of the refractive index contrast, we see a propagating mode, guided mode in between this core layer in terms of total internal reflection. Okay. And in this fiber, when you input this pump power as well as the weak signal, this pump signal will decrease over time, as shown in this red curve, and the signal power it will increase over time because of the stimulated emission over the length of the fiber. So if you want to find out what is the gain in this fiber, so this fiber have length. What is the length? Length is Z equal to L. And what is the so the gain formula? It is 10 log 10 P out divided by P. Okay. So the output power at Z equal to L is 1 milliwatt, and and the input power it is 1 microwatt. So that means the gain would it will be 10 log 10 1 milliwatt divided by 1 microwatt, which is nothing but, if you calculate it, it will come out as 30 dB. Okay. So this is how you can calculate what is the gain in a medium when you are given the input and output power signal. Okay. And the pumping power variation, this you can use it. You can use this formula to find out what is the power of the pumping power after certain length z. So Pz it will vary as Pz equal to 0 e to power minus alpha z. I think there was a problem in the assignment 4 where you can use this formula to find out what is the small signal gain coefficient. Okay, so please remember all this formula. This formula are highly useful to find out the solution to the problem. And the next, so the next is the optimum length of ADFA. So it's not like the gain if you uh, incident pump power as well as the signal power, the gain will remain amplified. The signal will amplified over all the length of the fiber. Not like that. So what you see, so initially we saw when we use pump, then the pump power will decrease over the length of the fiber, and the gain it will the signal power it will increase over the length of the fiber. If you see the red curve, it is increasing up to a certain length, that is L optimized to, and after that it is decreasing. So why it is decreasing? It is because at this after this length, what will happen? There is not enough pump power to achieve the population inversion. So if you see this schematic, we are using pump to excite these ions, erbium ions from ground state, from this ground state to the excited state. So the pump power will, it will be absorbed continuously over the length of the fiber. And what will happen after certain length? After this length, there is not enough power to pump the erbium ions from from the ground state to the higher excited state. So there is not enough power. That means we can't achieve population inversion after this length. So that is why we see that the signal power will decrease after this length. Okay, so it will decrease after this length, and the minimum power that is required for this maximum gain, it is denoted as the threshold pumping power. Okay, so the pump power should be this much. The pump power should be greater than P minimum to achieve the population inversion in the system and to achieve the gain in the system. Okay, and depending on the pumping power, we'll see different kind of curves. That is, if you see the solid line, these are the solid line for one type of pump, And these are the dotted line for another kind of pump. So if you increase the pump power, then the length at which the gain is maximum, it will also increase. Okay. So depending on the pump power, you will have different optimum length of EDFA. I think this is clear to you. So let us see what is the gain spectrum of EDFA. So the gain spectrum, if you see, it is not a flat line over the over all the wavelength. So you see there is an increase in gain, then there is a flat line around this, around 1550 nanometer. So the flat line you are getting, it is because of the Stark effect. So because of the Stark effect, you will see there is a multiplets of energy level, and because of that, you will see different resonance frequency. Okay. So because there is a spreading in resonance frequency, we'll see flat lines in the around the wavelength 1550 nanometer. So and this is how the gain curve varies with respect to the input signal power. So initially we've seen one formula, that is the how the saturated gain coefficient varies with respect to the intensity. So it is gamma nu is gamma 0 divided by 1 plus I nu by I is. So initially we've seen a plot like this, right? So okay, let me draw it again. So initially we had gamma nu varying like this. So for minimum intensity, it remains constant. Then after some intensity, it will decrease. And for EDFA, what is the gain curve? If you see the EDFA, it varies with respect to the signal power. The concept is same. When you increase the intensity, the gain will decrease. So if you see this, the top curve, it is around minus 40 dBm, which is 100 nanowatt. And the second one is minus 20 dBm, which is 10 microwatt. The next minus 10 dBm, 100 microwatt, and the last one is 1 milliwatt. So as we are increasing the intensity, the gain curve is gradually decreasing over time. Okay. So depending on the intensity, we see different types of gain curve. And the gain curve, it remains constant up to around the 1550 nanometer. We see a flat gain curve. It is not actually flat, but around 1550 you will see a flat gain curve. And the gain spectrum width, if you want to take approximate value, it is around 40 nanometer of flat gain. And it also changes with respect to input signal power. Okay. And this is one of the plot that is done experimentally. So if you see the power, the signal power is varied from 8 microwatt to 505 microwatt. So if you see the curve, when we increase the signal power, the gain is gradually decreased over time. Okay, and these are already for this is the formula for the saturated gain coefficient, which is gamma 0 nu divided by 1 plus I nu by I. So when we increase the input signal power, the gain will gradually decrease over time. Okay. So these are nothing new. So let us quickly move to the next slide. So the gain curve, this is the plot between the gain versus output signal when you have different types of pump power. So if you increase the pump power, the gain will also increase. Okay. So initially the graph is like this. So when you increase the pump power, the gain will also increase. Now for EDFA, you see the around 1550, you will see a flat band. So for this reason, we see a flat region then the gain will gradually decrease because of the increase in intensity of signal power. Now, when you increase the pump power, then the gain curve will increase and we'll see a flat line. Then after a certain point, it will start to decrease. Okay. So, and this is the schematic of a wavelength division multiplexer. So, if you see, multiplex means it will allow the propagation of different types of wavelengths simultaneously and effectively. It's not like some wavelengths are coupled more as compared to the other wavelength. Each wavelength is coupled equivalently in this multiplex system. And demultiplexer means we are separating different signals. So lambda 1, lambda 2, lambda 3, or lambda 3, we coupled to this fiber, which may be ADFA, by using multiplexing, and we separate it using the demultiplexing coupler. Okay. So in this way, we can increase the total capacity of the system. Total capacity means we can allow the propagation of different type of signals simultaneously and effective. And as you know, ADFA is widely used in communication system because of this flat line. So that means different types of wavelength can propagate with same gain around this in the ADFA fiber. Okay, not like one signal is propagating or the gain of one signal is higher than the gain of second signal. It's like a flat line. So we'll see same gain around different wavelength. Okay, so in this way we can increase, we can allow the fiber to allow the propagation of different type of signal simultaneously and effectively. So this is all about the gain medium. So previously we have gone through the NDR laser. Then we talked about ADFA. So this is all about the gain medium that we can use in a laser system. So next we'll discuss the resonator, which is used as a feedback circuit for the amplification process. So before that, is there any doubts in the slides of ADFA? Otherwise, we'll solve few problems, then we'll move on to optical resonator. So is there any doubt? Okay, so let us move to the problem then. So the first problem is this simple question. So if you know the concept, then you can easily solve. So it is based on the energy notation. So let me read out the question for you. So the problem is, which one of the following sets of quantum number corresponds to the atomic energy level 4 pi by 2 in the NDR material system? So and these are the four options. Okay. So if you see the standard notation for the energy level, it is 2s plus 1 L Z, right? So if you see the standard notation, it is 2s plus 1 L Z. For 4f pi by 2, what is the s? 2s plus 1 is 4. So that means s is 3 by 2. So s is 3 by 2. And for f, what is the L we are having? For f, it is L equal to 3. So that means the J value it can take from L plus S to L minus S. It's a vector sum of the angular moment, orbital angular momentum and spin angular momentum. So it can have values from L plus S to L minus S in steps of 1. So if you see the notation, so S is 3 by 2. S is 3 by 2 And what is the value of L? L is for F, it is 3, and J value, it is directly written, it is 5/2. So that means the option will be 4 option, which is S equal to 3/2, L equal to 3, and J equal to 5/2. So please remember how the energy levels are. These are described in terms of the angular momentum, the quantum number 2s plus 1 L Z. Okay. So let us move to the next problem. So last problem, it is based on the transition, metastable transition. Go through the question once. So the question says, in a particular transition, which of the following include a metastable state transition? So there are different type of transition that is given in the option. Now the question is asking which one of these transition include a metastable state. So how you can identify which one is which include a metastable state? So if you recall the metastable state, they do not follow the selection rule. So what are the selection rules? So selection rule allow the what kind of transition that can be possible in a atomic system. So for if you from quantum mechanics, we saw that the selection rules are delta S is 0, or delta L should be 0 or plus or minus 1, and delta Z should be 0 and plus or minus. It was a problem. So my screen is visible, right? So there was a problem in between. Okay. So for this problem, what you have to see, you have to check in which transition the metastable, the selection rule is not obeyed. For that, if selection rule is not obeyed, that means you can tell there is a involvement of metastable state during this transition. Okay. So if you see the first transition, which is from 4f 7/2 to 4g 9/2. So S for if you see 2s plus 1 is same for this both the levels. It is 4 4. That means the value of S will be same. So S value will be 3/2. So that means delta S is already satisfied. Delta is 0. And if you find out L, for F, L is 3, and for G, L is 4. So that means delta L is 1. So this transition follow the selection rule, right? So you have to check both condition, delta S as well as either delta L or delta Z. So you have to check two conditions, delta S whether it is equal to 0 or not, and delta L whether it is 0 or plus or minus 1 or not. Either delta L or delta Z. You can check. And let us see the second transition, which is 4D 5/2 to 4F 5/2. So if you see the S value is same because 2S plus 1 is same in both the transition. So S is 3/2 for both the cases. That means delta S is 0. And for D, L is 2, F, L is equal to 3. So that means the delta L, it is 1. So this transition also follow the selection rule, right? So for the third transition, 4H 9/2 to 4I 11 by 2. S is already same, that is 4 to 4. So that means S is 3 by 2. Delta S is 0. And the value of L, for H, L is 5, and for I, L is 6. So that means delta L, it is 1. So that means this also follow the selection rule. Okay. Now if you see the fourth one, fourth option is 4F 3 by 2 to 4I 7 by 2. So S is same because it is 4, 2S plus 1 is 4 here. So S is 3 by 2, delta S is 0. If you see L, for F, L is 3, and for I, L is 6. So that means here the delta L is 3, not 1, not plus and minus 1. So that means these transition, they do not follow the selection rule. So that means you can tell this transition include a metastable state during the transition. Okay. So you can see here how a simple concept can help you to find out the what is the whether there is a involvement of metastable state in this problem or not. Okay. Just you have to remember metastable state, they do not follow the selection rule. In this way, you can find out what is the transition which include metastable state, which is fourth option here. Now let us, I think this problem is clear to you. If any of this, if you have any doubt, any simple, no matter how small the doubt is, feel free to ask to me anytime. Feel free to stop me anytime and ask your doubt. So I'm assuming that this problems, all these problems are clear to you. Otherwise, you can ask me in the chat box or as well as you can unmute yourself and ask me anytime. Okay. So let us move to the next problem. So go through the question once. So let me read out the question for you. So it's a graph is given. There is a graph. So this graph shows how the pumping signal as well as the pump power as well as the signal power, how it is varying with respect to the length of this length of the ADFA file. So the question says the variation of pump power and signal power with length which is along the z-axis for a EDFA comprising fiber length 50 meter. So the length of the fiber is 15 meter and there is a variation of pump power and signal power along this 15 meter length of EDFA. So this is shown in this figure. Now the question is, it is asking about what is the threshold pumping power and signal gain in the ADFA. Okay. So threshold pumping power, as we see, it is the minimum power that is required to achieve a population inversion, right? So where can you get the threshold pumping power? So if you see in the graph, so if you see around this, the maximum signal power length below this maximum signal power, the signal power is decreasing. So that means signal power is decreasing means the population inversion is now decreasing over the length. So you can find out the threshold pumping power by taking the intercept of this, by finding out what is the okay. So if you want to find out what is the uh, pumping power, threshold pumping power. Okay. So we have to take the what is the pump power at this maximum signal power. So if you see this maximum signal power, it is intercepting at this level. And the pump power around this maximum signal is 15 milliwatt, right? So that means the threshold pumping power, it is 50 milliwatt. So you just have to see what is the pump power around the maximum signal power. Okay. So that means the pump power is 50 milliwatt. Now the signal gain. So for the signal gain, you can use the formula. Gain is 10 log 10 P out by P. So the P out, that is the output signal power after Z equal 15. It is, if you see the graph, it is 300 microwatt. And the input power, it is initially it was 30 microwatt. So if you put 300 and P out is P out is 300 microwatt and P in is 30 microwatt. So if you find out what is the gain, so gain will be 10 log 10, 300 by 30. So that means it will be 10 dB, right? So in this way, you can find out what is the gain as well as what is the threshold pumping power that is required to amplify the signal. So is this clear to you? These two solutions? Otherwise, we'll move to the next part. Okay, so I think there is no doubt in this problem. Then let us move to the next part. So next part is, if the EDFA is to be operated at the maximum gain, then the fiber length must be reduced by how much meter? And what is the maximum gain of meter? Microwatt around Z equal to 11 meter. The PL is already 30 microwatt, but 10 log 10, 450 by 30. So if you calculate it, it will come around 12 dB. So the maximum gain that you can achieve in the EDFA is, in this EDFA system is 12 dB. And to achieve this maximum gain, we have to decrease the length of EDFA by how much meter? 4 meter, right? Because the total length of Z, the EDFA was 15 meter, right? So if you see the graph, the length of this EDFA, it is 15 meter. But we are getting maximum gain around Z equal to 11 meter. So that means we have to decrease the length by 4 meter to achieve a maximum gain. Maximum gain in the output. Okay. So this is how you can approach this problem. So is this problem is clear to you? All these four, I think I have solved 3 problems. So do you have any doubt in these 3 problems? Otherwise, let us see one additional problem. Okay. So let me ask. It's a true and false problem. So it is given the energy spread of metastable state is broader than the energy spread of other energy levels. So one option is this statement is true, other option is this statement is false. So it is asking the energy spread of metastable state is broader than the energy state of other energy. So how you can approach this problem? So if you recall the metastable state, it doesn't follow the selection rule, right? So that means the atoms that is populated in this state will try to occupy the state for a longer time. So the lifetime of this metastable state, it is normally greater than the lifetime of other state. To see metastable state, it is greater than the lifetime of other state. And the energy spread, if you recall the lifetime, so delta nu. So delta E and delta nu go to H cut. Sorry, delta nu, delta T, right? So that means the energy and delta T is nothing but tau L lifetime H cut. So tau L is, sorry, delta E is, that is the energy spread. It is inversely proportional to the lifetime. So as you see, the tau L of metastable state is larger than the tau L of other energy level. So that means the delta E, it is narrower than the other energy level. It is not broader than the energy level. So that means this statement is false. Okay. So these are some of the basic problems that covers ADFA as well as the broadening problem also. Now let us move to the week 5 content. So in week 5, what we see, we basically study about what are the different type of optical resonator. So we have studied about pump, we have studied about the gain medium. Now we'll see what kind of optical resonator we can use in a laser system. Okay. So as you recall, the laser system has three components. One is the gain medium, other is the pump, and the third one is the optical resonator. So the gain medium with pump, they provide a amplification process, and the resonator, it acts like a feedback circuit so that the amplification remains for a longer time within this resonator. Okay, and we can take a we can compare this optical resonator with the electronic oscillator. So in an electronic circuit, the electronic oscillator, it acts as a source of radio frequency, right? In optical oscillator, it acts as a source of optical frequency. So in electronic oscillator, if you see, there is an amplifier and there is a pump that is fed through this voltage, and some part of this output, it is fed back to this amplifier using the feedback circuit, so that we can see a stable output of this amplifier signal. Okay. Similarly, in optical oscillator, we have pump, which is 980 nanometer for the ADFA signal, sorry, for the ADFA fiber, and a active medium. So we see different kind of active medium, NdArc, ADFA, ND glass, and we have optical resonator, which typically consists of two mirrors. One has reflectivity of 100% and other one is reflectivity of 90%. So now we'll see what are the different types of optical resonator that we typically use in a system. Okay. So you can classify the optical resonator in two types. One is open resonator and another one is closed resonator. Okay. So if you see the open resonator, it consists of two mirrors, that is M1 and M2 separated by a distance L. So, and in these two mirrors, what will happen? The light that is incident on one of the mirror will get reflected back to the other mirror, and they will oscillate back and forth in between this M1 M2 mirror. So what will happen? You will see a standing wave pattern in this two mirror. Standing wave means the light, the energy don't propagate. They stands in between this two mirrors. That is, this they are stored and they are confined in between these two mirrors, M1 and M2. And if you see open resonator, so if other than this path where the light is perpendicular to the mirror, if you see a ray that is traveling, making an angle in this mirror. So what will happen to this oscillation? This ray, they will eventually escape out from this open resonator. Okay, so they are not confined in this two mirror. Now, if you see the closed resonator, so in contrast to the open resonator, the closed resonator, light is confined over a volume. So open resonator, the light is confined over a length, but in a closed resonator, the light is confined over a volume. So that means the number of modes, that is the number of wave path, that is the ray that is propagating parallel to the mirror or making an angle to the mirror. So it will be allowed in the closed resonator case. So the number of resonator for this, so number of modes or number of ray paths that is possible in the closed resonator, it is greater than the open resonator. So if you want to find out what is the number of photon state, that is number of modes between frequency nu and nu plus d nu, it is given by this formula. M nu d nu equal to 8 pi nu square d nu divided by nu VQ. So don't get confused, it is not nu q, it is VQ, velocity, which is equal to C by N. Okay. And for the open resonator, it is given by 4 by C d. So what we have seen? We have seen that the number of modes in a closed resonator, it is typically greater than the number of modes in a open resonator. So, so what is the practical implication of this system? So if you look at the open resonator, so number of modes is small. So that means here, if you make a laser out of an open resonator, the line width of the laser, it will be narrower because the number of modes are less. But if you take a closed resonator, the number of modes are higher. That means there are many resonance frequency that is oscillating in the closed resonator. So that means you will see a broader line width for a laser source which is closed resonator. So because, and we want that the typical, if you recall, the lasers are highly monochromatic. So that means we use open resonator for a laser system because we want the light should be as monochromatic as possible. So that is why we typically use open resonator in the system. Okay. And what are the different types of open resonator? So there are 4 different types of open resonator. One is plane mirror resonator, where and other is spherical mirror resonator, ring resonator, and fiber resonator. So if you see this plane mirror resonator, so it typically consists of 2 plane mirrors that are separated by a distance L. And if you see the red curves, that is propagating perpendicular, that is normal to the mirror surface. So they are oscillating back and forth in between these two mirrors. So that means this ray path, it is highly confined in between this plane mirror resonator. And if you take a ray path where the ray is making an angle with respect to the mirror. That is, if you see this path, so it is making an angle with respect to the mirror, right? M1. So this, if you see the ray path, it oscillates in between this mirror and it eventually escape out from these two mirrors. So that means this ray path is not allowed in the plane mirror resonator. Screen is not visible. So okay, so the screen is freezed now, I think. Okay, so let me reconnect then. Please wait for 1 minute. So I think now the screen is visible, right? So it got frozen for a few minutes, I think. Okay. So we're discussing about what is the different types of open resonator. So, okay, let me quickly, because the screen was frozen, let me quickly go through the concept that I told earlier. So we have different types of optical resonator. One is open resonator and another one is closed resonator. So if you see the open resonator, there are only few ray path that is allowed to propagate in this open resonator. But if you see a closed resonator, because the light is confined inside the volume, we have different type of ray path that can be confined in the closed resonator. And what is the difference between this open and closed resonator? If you see the line width of laser in open resonator, so open resonator has narrower line width and closed resonator has broader line width. So that means if you want to construct a laser, it's better to use a open resonator because the line width is narrower. So the light will be monochromatic. It will be highly monochromatic in case of open resonator as compared to the closed resonator. Okay. And if you want, so we have different types of open resonator. One is plane mirror resonator, spherical mirror resonator, ring resonator, and fiber resonator. So if you see the first case, which is plane mirror resonator. So if you see the red lines, these lines are the ray path that is propagating perpendicular to the mirror surface. So if you see this red path, they are highly confined in between these two mirrors. Now, if you take a different ray path that is making an angle with respect to the mirror M1. So if you take this path, you can see the path will follow a zigzag step, then it will eventually escape out from this mirror surface, from the resonator volume. Okay. So that means in the plane mirror resonator, only few ray paths are allowed. If you see a spherical mirror resonator, so in the spherical mirror resonator, you can see there are different type of ray paths that can be possible inside this spherical mirror resonator. So it consists of two spherical mirror which have radius of curvature R1 and R2. And you can see the ray path that is, if you incident a light parallel to this mirror, it will go through this focus point and it will oscillate inside this spherical mirror resonator and it will be confined inside this spherical mirror resonator. And the other kind of resonator is the ring resonator. So ring, if you take a simplistic picture is, it consists of three mirrors at an angle. So if you see this figure, if you incident a light in this way, the light will propagate in a resonator path. So the light follow a resonator path and it is confined in between this 3-mirror setup. So this is the ring resonator setup. If you and other type of setup is where we use waveguide and ring resonator to couple the incident power to a ring resonator. So if you see this third figure, so it is one waveguide, which have refractive index N1, and one ring resonator and another waveguide here. So when light is incident through this waveguide, what will happen? So at this point where the ring resonator is closer to the waveguide, the light will get coupled to this ring resonator and it will oscillate inside it, either clockwise or anti-clockwise. It will oscillate inside this ring resonator, and in each oscillation, what will happen? Some power will again couple to this waveguide, and we will get a non-zero power in this input port of this second waveguide. Okay, so in this way, you can use a waveguide and ring resonator system to confine a power or to oscillate the power over time. And the other type of open resonator, it is a fiber resonator. So similar to the ring resonator system, here you use optical fiber, which is nothing but a core cladding interface, where we see total infrared reflection, uh, which will help in guiding of wave in this length of this optical fiber. So when you feed optical power through this input end, then it will eventually come out to this output end. Okay. So it is confined in the core cladding, in the core layer by means of total incident reflection. So in this course, we'll take different types of approaches. One is ray optics, one is beam optics, wave optics, and Fourier optics. So using these different type of approaches, we will see how the optical resonator, how the different parameters are defined using the different approaches. And for the first one, the ray optics approach, if you see this figure, so this is the ray confinement picture. So if you see, it consists of a confocal. If the first figure, it consists of a confocal mirror resonator. So confocal, it means these two mirrors have same focus. Okay, so that means this, if you take two confocal mirror, so the focal point, they coincide. So that means it is the coincide, it is the center point. So this means this is the focus point for this first mirror M1. This is also the focus point for the second mirror M2. So you can relate this focal point to the length of this resonator. So total length, it will be F1 plus F2, and F1 plus F2 is same. So that means the total length will be 2 times of F. Okay. And for a spherical mirror, what do we have? For a spherical mirror, we have F equal to R by 2. Right? Let me see the relation first. So we have F equal to R by 2. So that means you can write it as L equal to R. Okay, for the confocal mirror resonator. And the other type of ray confinement is in a concentric mirror resonator. So in a concentric mirror resonator, we have, instead of same focal point, we have same center of curvature. Okay, so that means the radius of curvature are same for this two types of mirror, M1 and F2. So we have to plot it. So if we have concentric mirror, the radius of curvature of this mirror is same as radius of curvature of this mirror. So the length between this mirror, you can write it as R1 plus R2, which is R1 and R2 are same, that means it is 2R. Okay. So this is the concentric mirror resonator. And in the so if you see in these two figures, so the diffraction of the beam. So whenever there is a light that is propagating, so we'll see a diffraction. So and here in the beam confinement picture, we'll see the diffraction is compensated by the focusing effect. So if light is trying to bend in this surface, then because of the focusing effect of this mirror, it will be reflected back to the resonator surface. Okay. So the diffraction effect, it is compensated by the focusing effect of this mirror. So I think these all are clear to you. Till now, do you have any doubt in the concept? Okay. So let us move to the next part. So now we'll see different types of different parameters that characterize a resonator. So how we can characterize different types of resonator based on its resonance frequency, nu q, and free spectral range, resonator loss coefficient, fineness, which is also related to the quality factor, and transverse mode, which describe the allowed field distribution. So for the first one, let's say we have a plane mirror that is the which is surface M1 and mirror M1 and M2 and separated by a distance L. And we are seeing a confinement of plane wave in between these two mirrors. So plane wave, you can write it as, this is the expression for a plane wave. So for a plane wave, you can write the expression as A e to power I kz minus omega t. And you can also write it as A e to power I phi. So phi is the phase of the propagating wave. Okay. And for resonance, what we have, this is the resonance condition. So for resonance to occur, resonance means the light is confined in between these two mirrors. So for resonance to happen, what we have? We have the phase difference. That is the phase that is accumulated in the round trip. It must be integral multiple of 2 pi. Okay. So we have a mirror, two mirrors M1 and M2. So now the rays propagating like this now and it get reflected back to the mirror M1. So it is one round trip. So for light to be confined in this mirror, what we have in this total round trip, in this round trip, the phase that is accumulated, it should be integral multiple of 2 pi. And how you can calculate the phase, the accumulated phase, if you have a given length L. So you know that if you recall from the optics, for when the wave travels lambda distance, the total phase accumulated is 2 pi. Okay. So when the wave covers a distance lambda, the phase accumulated is 2 pi. Now, what is the total distance in a round trip? So here you can see the distance between these two mirrors. It is L, right? And for the round trip, the distance covered is 2L. It get reflected back. So that means if you want to find out what is the phase accumulated in the round trip, so you need to find out using the 2L distance. So lambda, the phase accumulated is 2 pi. And for 2L distance, what is the phase accumulated? It is 2 pi by lambda into 2L, right? And 2 pi by lambda, you can, for a medium, if it is not in free space, let's say in between the mirror, there is a medium, which is refractive index L. So for this case, you can write lambda as lambda 0 by n. So you can write the total phase accumulated as 2 pi lambda 0 n to n. So this is the total phase that is accumulated in a round trip. And this is also written here. Okay, 2 k0 and n. So k0 is 2 pi by lambda 0 or omega by c or 2 pi nu by C. And if you rewrite K0, what you will have? You have the resonance frequency nu Q equal to Q C by 2N. So this is the resonance condition. Okay. So this is the resonance frequency of a plane mirror resonator, which also form a standing wave. So let us quickly show what is a standing wave. So standing wave is like the energy do not propagate beyond this cavity. So if you have a mirror L and there is a standing wave, so light is constantly oscillating back and forth in between this mirror. So because of this constant deflection, we will have standing wave, and the standing wave can be of different types. So depending on the mode, you have different types of standing wave. So the fundamental mode in between this mirror, it will be of this picture. So this is the fundamental mode where the light is propagating, light is covering lambda by 2 distance. So you know that for a wave, this distance is lambda, right? So this distance is lambda by 2. So for this fundamental mode, what you have? L is lambda by 2, right? And the next higher order mode will be, this is for Q equal to 1. So Q basically represents what is the mode number. So the first is Q equal to 1. For the second case, what you have? You have lambda distance that is covered in between these two mirrors. For the reflected wave, you have this part. And the length is constant, right? So for this mode, what we have? L equal to lambda. And Q is 2 here. Similarly, so Q2 you means there are two lobes. Lobe 1 and lobe 2. And Q1 means there is only one lobe, which is this one. You can understand this way also what is the Q exactly in this system. And for Q3, you want to find out what is the ray confinement picture. It will be this way, right? Instead of now 1, so this is, for this it is lambda by 2. For this it is lambda by 2 plus lambda by 2, which is lambda. And for this one, it is lambda by 2 plus lambda by 2 plus lambda by 2. That is 3 lambda by 2, right? And this is the reflected part. And what is the Q value? Q is 3 here. So this is the some basic ray confinement picture of a standing mode in between two plane mirror resonator. Now, if you see the resonance frequency nu Q, it is given by this formula, which is Q into C by 2N. Now, if you want to find out what is the next frequency, that is nu Q plus 1. So this is nothing but Q plus 1 C by 2N. So if you want to find out what is the difference between these two frequency, what is the separation between this frequency, so you just have to take the difference between nu Q plus 1 and nu Q. And if you see, it is a constant, that is C by 2N. So this difference, the difference between two conjugative resonance frequency, it is known as free spectral range. Okay. This is the parameter that is used for the resonator. Free spectral range, which indicates the separation between two conjugative frequencies. Now, if you see the expression, so nu f it is equal to C by 2N. So that means it is the free spectral length depends on constant C, which is always a constant speed of light, refractive index N, and the length of the fiber. So for a given length of the optical resonator, the nu f will remain constant, And as you increase or decrease the length of the resonator, the free spectral length will decrease. So this is the schematic of a spectrum profile. So you have three resonance frequency, nu q, nu q plus 1 and nu q plus 2, and the separation between them is the free spectral range, which is equal to C by 2N. Okay. Now if you want to find out what is the typical value of a normal day-to-day laser. So if you take lambda equal to 600 nanometer, which is around the red wavelength, red light, and for L, L equal to 15 centimeter and N equal to 1, what you will get, the Q value, it is much greater. It is of the order of 10 to the 5. So for a typical optical resonator, the Q value is very, very high. It is a value of 10 to the 5 order. Okay. Not like it is a value of 1, 2, 3, 4. So the Q mode number is very high. Now if you see the spectral response, that is how the intensity profile with respect to the frequency. So if you see around the resonance frequency, the intensity will be maximum. So if nu q plus 1 and nu q plus 2, if these are the resonance frequency, then the intensity will be high for this frequency. But in addition to that, what you will see around the frequency that is adjacent to this resonance frequency, we'll see this. You will see a spreading of pattern here. Okay, this spreading of pattern, it is because of the resonator loss. We will see what is the resonator loss in our next slide. So, so these are the same concept, that is the resonance frequency. It is given by QC by 2NL. And if you want to find out what is the free spectral range, it is nothing but the difference between the resonance frequency is given by C by 2NL. And the FSR, the free spectral length, it is inversely proportional to the length of the optical resonator. And the spectral response, that is the intensity profile, is a function of frequency. If you see, there is a line width around this resonance frequency. And this line width, it is due to the resonator loss. Okay, because of some losses in the resonator, we'll see that there is a spreading of pattern here. Now we'll see how what is the line width of a typical resonator. So let us take a passive resonator. So passive resonator means there is no active medium in the system, that is there is no gain medium. So we are just seeing what is how the light is confined in this two mirror. Okay. So these are two mirrors, M1 and an M2, which are separated by a distance L. And if you see, if U0 is the initial field. Okay. Initial field. Now after one round trip, that is when light incident on this mirror M2 and it get reflected back to the first mirror M1. So after one round trip, we are saying U1 is the field after one round trip. Okay. So U1, you can write it as H times U0. Right? And H is, you can write it as in terms of the attenuation factor, that is one is the amplitude attenuation factor R, and one is the accumulative phase during one round trip. So phase, as we have already seen, you can write it as 2 times K0 NA. So this is the phase formula. Okay. So this is the phase expression. Now, if you want to find out what is the field after two round trip, that is U2. So U2 is nothing but S times U1. Okay. So U1 you already know, it is S times U0. So if you put it, you get U2 is H square times U0. And the total field that you will get through this passive resonator, it is u0 plus u1 plus u2 plus u3 dot dot, right? And if h is much less than 1, you can approximate this expression, that is 1 plus h square. You can approximate is as 1 divided by 1 minus h. And if you want to find out what is the intensity profile, so intensity is nothing but square of the amplitude, right? So it is square of u total. So you just have to put the expression u0 square is you are taking as I0 and 1 minus h. So take the expression of h equal to r e to r minus I5 and put it in this expression. So if you put it, the final expression you will get is I equal to this expression. Now this is the variation of intensity with respect to the phase of the accumulated phase of the confined mode. Now for the spectral response, we typically plot it in terms of intensity versus frequency. So next what we have done, we have defined a parameter, that is f equal to, this is the fineness. Okay. So fineness, it is, you can express the fineness in terms of the reflectivity of the mirror, reflection coefficient of the mirror. So fineness f equal to pi root 2 1 minus r. If you put it and use this expression, the expression for the accumulated phase, which is 2 pi nu by nu f. So what you get the spectral response as a expression like this, which is nu max plus divided by 1 plus 2f by pi square sine square pi nu by nu f. Okay, so this is the expression of spectral response. We'll see what are the characteristics of the spectral response. So before that, so you must have known vector and scalar, right? So vector f, it's a quantity that is magnitude as well as direction, and scalar they have only magnitude. Similarly, we can define a parameter, a quantity which is phasor. So phasor, similar to vector, it has magnitude and phase. So if you see the electric field expression, this is the expression for plane wave, right? A e to power I omega t minus kz. So if you see, there is a magnitude here and there is a phase here. So this expression is for the phasor expression. Okay. And to plot this phasor profile, what do we take? We take a reference. So we take a reference of 0, that is phi equal to 0, and we plot the phasor, that is the angle phi that is having with respect to this reference line. So A here is the magnitude and phi is the phase angle. Okay, around the total phase after one round. Now, similar to vector addition, we can also follow a phasor addition. So for phasor addition, what do you take? We take a reference line, which is phi equal to 0, and plot the first phasor, that is, let's say phasor 1 is A to power minus I phi. So this is the magnitude and this is the angle. Now for the second phasor, which is phi 2 equal to d e to power minus I phi 2. So we put the tail of this phasor in the arrowhead of this first phasor. Okay. So put B here. So this is the magnitude and this is the phasor angle. And this angle is the total phase accumulated over this phasor phi 1 and phi 2. So these are some concept of phasor. Now if you see, so let's take two different cases where in one case we have reflectivity which is equal to 1 and other case reflectivity is less than. So reflectivity equal to 1 means the losses of this mirror, they are less. So there is the losses are less. So we typically assume as a lossless mirror. And when R is less than 1, it means there is losses in the mirror after reflection. Okay. So if you see the first one, the first case where r equal to 1 and phi is not equal to 2m pi. So u1, you know it is s time u0 and h is r e to the power minus I phi. And if phi is not equal to 2m pi, and if r equal to 1, then you have u0 e to the power minus I phi, right? u1 equal to u0 e to the power minus I phi. And if you take the magnitude, u1, the magnitude of u1 is also equal to the magnitude of u0. So that means when you plot the phasor diagram, the magnitude after one round trip, second round trip, or third round trip, they have equal magnitude. But the angle, the phi, but there is a angle phi. Okay. So this is, let's say this is u0. So this is now u1, which is u0 times e to the power minus I phi. This will be u2, u3, u4, u5, u6, u7. So if you see what is the resultant phasor here. So if you see after third round trip, let's say this is first round trip, second, third. So after third round trip, the resultant will be the blue curve here. Here you can see there is no building of intensity in this um, profile here when phi is not equal to 2 is not equal to 2m pi. So resultant, it varies and it is not building up over the round trip. Now if you see, take another case where pi is equal to 0 and 2m pi, 0 or 2m pi. So for this case, if you write down u1, so u1 is u0 e to the power minus I phi, right? And if so for this case, the magnitude are same because r is 1, right? And in addition to magnitude, if phi equal to 2m pi or 0, that means this term is 1. So this term is 1 means u1 is equal to u0. That is, all these phasors, they are oriented along the same direction. So that means they are oriented along the same direction means they will build up after first round trip, second round trip, third round trip. Okay. So this is what's shown in this figure. So when you have r equal to 1 and phi equal to 0 and 2m pi, there is a building of intensity or the amplitude or the signal over time. Okay, so they are oriented along the same direction and they will build up after sufficient amount of or after one round trip, second round trip, third round trip. And in the second case, which is the practical case where r is less than 1, that is there is a losses uh, there will be loss when the light will reflect from the mirror. Okay. For this case, what we'll have? We will have this magnitude not equal to u0. So that means the amplitude, it will vary over time, vary over round trip. Okay. So if you see this figure, you can easily see the amplitude is gradually decreasing over time. And there is no building of, there is no um, building up of amplitude over the round trip of the propagating wave. Now in the second case, that is when phase is 0 or 2m pi. So for this case, we will have, although this u1 magnitude is not equal to u0, these are not equal, but the u1 and u0, these are oriented along the same direction. That means when the wave when they cover the round trip, they will add up in the same direction. So that means there will be building of intensity or building of profile in the optical resonator. Okay. So the second one is the more practical case, which we typically observe in a laser resonator. Now let us quickly see how does the spectrum or a spectral response looks like. So this one is already derived in the previous slide. So I know is written as this. So if you see it is a square function, that means you will see a symmetric function of this spectral response. So that means there is a line width around this resonator frequency. So to find out the line width, what you have to take? We have to take the line width at half maximum of the intensity. Okay. So for that to happen, that is I nu. Okay. Now I think they have discussed about the Imax first. So for I nu equal to Imax, what we have? This term, second term is 0. So that means 2f square sine square I nu by nu f equal to 0. And this will happen when sine square, this term pi nu by nu f, that is, this will happen when this angle pi nu by nu f, it is multiple of pi, right? So that means the nu is equal to m times nu f or q times nu. So this is the resonance condition. So this is where you can get maximum intensity of the spectrum. So this is the resonance frequency, and for the off resonance frequency, that is the midway between them, that is around the line width. Okay, around this line width where we are seeing. Okay, so before discussing the line width, let us discuss what is the location of the minima point. Okay, so for the minima, what we have, the angle nu pi nu by nu f, it must be equal to odd multiple of pi by 2, that is q plus half. So that means nu is q plus half nu f. So these are the location of minima and maxima in this spectral response. And this is one of the example where to calculate what is the ratio between the minimum intensity and the maximum intensity of the spectrum profile. So if you take, let's say we take a round trip loss of 10%. That is, in each round trip, the intensity becomes 10%. So that means the losses, that is r square, it is equal to 1 minus 0.1. So it will be r square equal to 0.9. And so this next one is just an example. So instead of 10% loss, if we have 19% loss, then in that case, the r square will be 0.81. And if you are given r square, so if in the problem, let's say we are given r square, if it is given, then you can easily find out what is the fineness pi, f. So f is given as pi root r 1 minus r, right? Yes. Nitish, you can ask your question. Hello, Nitish. You want to ask any question? So when you have, you can write it in the chat box. So in the meanwhile, I can. So let me go through. Okay, please unmute. Sorry, I forgot to unmute everyone. Okay, now you can speak.
Yeah, ma'am. Actually, here round trip loss is 10%. So in that case, we have to use this equation for fineness f equal to pi r to the power half 1 minus r. We have to
Yes.
use approximate.
Yes. If it is already given the round trip loss, then you can easily find out what is the fineness. You can use this formula.
Okay, ma'am. Ma'am, we have one approximated formula.
That is when we have, I think this one, sine. So are you talking about this? No, not this one. This one.
Yeah, ma'am.
So this is the case where if in the, let's say the question R is given, right? Then you can easily find out what is the fineness of the system. And let's say R is not given, but instead of R, alpha R is given. That is the resonator loss coefficient. If that is given, then you can use this formula, right? Either of this you can use. Pi by alpha RL or pi root over R 1 minus R.
But ma'am, if you apply any one, so there is huge difference.
It's like there is a approximation that has been done here, right?
Yeah.
Pi by alpha R L. So that is why if you make an approximation, then you will get different answer. But I think depending on the problem, you can use if
Yeah,
the
I did.
problems requires
I our question.
what?
What is the limitation for the approximation?
So if you see this formula alpha R, when do you use this formula? If you look it, so let me go through the slide once. This thing. So so whenever we are making the approximation, please remember what is the approximation we are making. If that approximation is given in the problem, then we can use this formula. Okay. Otherwise, only use the initial formula. Don't use the approximate formula. So if you see this problem, it is
Ma'am,
given alpha.
in this
Yes.
PPT have pi by alpha RL are high fineness, and the range for high fineness is 0.90 to 0.99.
Hmm.
So, ma'am, if R square is in between these limits, then we have to apply this equation, or we have to apply general equation pi r to the power half 1 minus r.
Okay. For when R square is in between 0.9 to 0.99, as we are talking, this is high fineness laser resonator, right? So for this case, you can see when this R square lies between this, the alpha L is 0.02. So calculate the alpha L, and if the alpha L, you can easily see alpha L is much less than 1. It is around 2%, right? So
Yeah, ma'am.
in this case, you can use the approximate formula, which is pi by alpha R L. But if it is not, then don't use the formula. Just use the pi root over of R 1 minus R formula.
Okay, thanks.
So, so in any formula, if you come across, there are many approximation that we are doing. So please remember the approximation you are doing. Okay, don't use any form. So you can't use this formula here and another formula in that case. So just be careful of what is the approximation and the condition where we are achieving this formula. Okay, if it is satisfying the approximation condition, then you can use this formula. Okay, it is clear to you, Nitin? Okay. The next one is, so we are discussing about, here. So here you can see the R square is 0.81. It's not between 0.9 to 0.99 that we have seen this case. So if you see, this is for this condition to valid, R square should be in between 0.9 to 0.99. But in this case, it is 0.81, around 0.8. So use this formula of fineness, that is F equal to pi root over of R 1 minus R. Okay. So if you use it, you can, the fineness will come around 30. And from the fineness, you can easily use, and there is another example. So these examples are for practice. so that you can practice more and more. So if R square is 0.36, that is the losses in a round trip is 64%. So for this case, R is 0.6, and here you can also see R is not between 0.9 to 0.99. And for this case, use this formula F equal to pi root over of R 1 minus R to calculate the fineness. And once you got the fineness, you can easily calculate what is the ratio between the I min and I max. If the problem is asking about what is the ratio between I min and I max, then use this fineness formula, calculate the fineness from the reflectivity, reflection coefficient, and you will get a answer around 0.062. Okay. And these are some of the spectral response that are calculated numerically. Okay. So if you have how this I mean by Imax varies with respect to the different frequency. So if you take around nu q equal to 0.1 UF, so the intensity is 0.41, and as you move away from the resonance frequency, the intensity gradually decreases. Towards the resonance frequency, the ratio will be high, then gradually it will decrease over time. And the other one is the fineness. Okay. So if you different fineness, let's say F3 is greater than F2, greater than F1. So the spectrum profile, it will look like this. So as we increase the fineness, the response, the spectral response becomes narrower. And as we decrease, it becomes broader. Okay. So we'll stop for now. So there is a question in the chat box. Week 5 assignment, question 1. We have to choose incorrect option from 4 given options, but all options are correct as per my opinion. Please check the question. Okay. So if you are thinking all options are correct, then please raise a question in the discussion forum. Okay. I will also I will tell the NPTEL team about your query, but please try to raise the question in the discussion forum so that it will be recorded in the NPTEL team. So let me see whether you are talking right or not. So please raise your query in the discussion forum, and in the meanwhile, I will also talk with the NPTEL team regarding your query. Okay. Question 1. Any other query other than this? Question 4 in fifth week's assignment. What is your query? So let me unmute you so that you can ask. Question 4 in 4. Okay. So for that, please go through whatever I have discussed now. Okay, I have already discussed whatever the theory you are having. It is already answered in this live section. So please go through it. I can't tell the value of Q now because you have to figure it out, and it's the solution has not been released also. So I can't tell what is the value. So please go through the live section. You can easily find out what is the value of Q. In question 1, so let me please write down your query in the discussion forum. and as well as meanwhile, I will go through the question, and if it is sorted out, then we'll communicate it to you in the discussion. Okay. And any other doubt? Okay. If there is no other doubt, then let us close this section now. So, thank you for joining this section. I think, I hope whatever I have discussed, it is clear to you, and it is also helpful to you to go through the concept again and solve the assignment problem. So, let us meet on next Saturday, same time from 4 to 6. So, please try to join the live section. Uh, if you join it, then you can ask your doubts freely, as well as you can clarify your doubts also. So, okay, let us end the section for now. We'll meet on next Saturday. So, goodbye, everyone.